Hello everyone, and welcome to our first pre-lab that is going to involve this new quantity we defined yesterday, or called yesterday, the momentum, the mass in motion, the product of the mass and the velocity of an object. Now this was used by Sir Isaac Newton, and very often it's used to analyze collisions. So if an object's colliding, it may change its momentum during that collision. So how could we change that object's momentum? Well, if you look at the equation, there's going to be one of two ways. Either you will change the mass of the object, or you could change its velocity. Now, we're going to focus here not on changing the mass of an object. In this unit, we're going to generally look at systems which are known as closed. A closed system is one in which all of the mass remains constant. It doesn't change, if you will. So if we have, say, two carts colliding into one another, we're not going to lose a piece of the cart that's going to fly away on its own. If it does, we're going to keep track of it. All right? So we're going to keep track of all the mass. So that means that what we're talking about here to change an object's momentum is we have to change its velocity. And if you think back a few units ago, we know that in order to change an object's velocity, you must apply a net force. Right? Net force result in acceleration. They result in the velocity changing. So if we want to know then how much the momentum changes because of that force, we actually need to know a couple of things. Okay? And one is that not only how much force we apply, or net force in this case, but also how long we apply that force. Right? In most of the problems we've done up to this point, that force is applied throughout the entire problem. We pull a box across the floor, right? And so we're pulling on it the entire time. But what if we only pull on it a little while and then stop pulling? Right? What would happen during that time that we applied that force? How much would its momentum change? That's what we're going to look at in this lab. So the device we're going to use, first of all, we have a little cart with a plunger on the end here, little metal carts we've used before. Over here on this end, this is a device we've used, but not this way. It's hooked up to the track. This is a force probe. It's going to measure forces. And then over here, of course, we have our old friend, the motion detector, with which we can measure velocities. So basically what you're going to do in this lab is you're going to push the cart and let it bounce off of the force probe. Nice little springy kind of action there. So again, you push it, it bounces off the force probe. Now, while it's interacting with the force probe, while it is colliding with the force probe, there'll be a force applied to the cart, which will be measured by the probe. And then we can use the motion detector to measure the velocity before it collides and after it collides. Right? After it collides. And then we can compare these things. What in particular are we going to compare? Well, two quantities might not be fairly obvious to you now, but hopefully you'll see why I chose these after the lab. The first one is the area under the curve of a graph of force versus time. Notice how much force is applied over how much time, basically. This is a quantity that we call impulse. All right, so impulse is part of this lab. Impulse is how much force acting over a time. And then we're going to compare that to the resulting change in momentum of the cart. Now, how are we going to calculate a change in momentum? Well, as with all quantities, you find its change by taking the final minus the initial of each. Final minus initial momentum. Each momentum is, of course, a mass times a velocity. Notice how we don't have to subscript the mass because we're going to keep a closed system, constant mass. So we have mass times final velocity minus mass times initial velocity. Now, factor out an m, and we get mass times the quantity final minus initial velocity. But when you take the final minus initial of a quantity, you're really looking at the change in that quantity. So we can say change in momentum is final minus initial momentum. We can also say it's mass times change in velocity. This is handy for us in this lab because, as you're going to see with the program we're using, we'll be able to find the change in the velocity right off the graph. So let me show you how we're going to measure both the impulse, the area under the force-time graph, and the change in momentum, mass times change in velocity, using the program. So the program here essentially consists of two graphs. Okay? The top graph is a graph of force versus time. Right? That's reading what the motion detector is doing. The bottom graph is a graph of velocity versus time. So this is what the motion detector is showing. Okay? So first of all, let's look at the velocity time graph. Here's where you're pushing the cart. Right? You're pushing it, you're getting it going. Here is where it's moving towards the motion detector. Here's where it's moving away from the motion detector. I'm sorry, back towards the motion detector, I should say. Notice the way I've got this set up, here is that when it's moving to the left in our picture, that's a negative velocity. When it's moving back towards the right, that's a positive velocity. Now, we need to know the change in the velocity so that we can calculate mass times that, which is the change in the momentum. Well, right here we've got this little examine tool. Hang on. So right here we've got this little examine tool. If we take this examine tool and move it right down to before the collision, okay, this right here would be the velocity of the cart, roughly negative 0.60 meters per second. This is the time, right? Because it's y, x, right? X comma y. So this is the velocity of the cart. Now, we could just move this up here and figure out what the velocity is after, and then do final minus initial. But there's this cool thing you can do with this program. If you go to the corner of this, you see how it turned to the hand, and you see that little delta there? Remember, delta means change in. So watch what happens here. If I grab the corner, I can pull this, and then look what it's doing here. It's showing me change in x across and change in y up. So if I choose the point I want, it kind of locks onto the point, like right about there. Okay? You can see that the collision took a little over 1/10 of a second, but then this right here is the change in the velocity, a positive 1.12 meters per second. It changed from negative 0.62 to what I'm guessing up here is about a positive 0.52, right? But we can get this right off the graph here. It's kind of cool. Now, area under the force time graph is the impulse. I've already got this little area box turned on here, so all we have to do is select, click and drag, over the part of the graph we want. And now that's the area under the curve, 0.57 Newton seconds, right? Newton seconds. So it's actually figuring out this little spike here. What it's really doing is counting up the little boxes that's on here, each box, and then it's doing the fractions of the boxes. Right? Kind of like if you remember our area of a circle lab we did at the beginning of the year. Right? So the computer's just doing that very quickly. Now, it's important that you select the part of the graph that you want, because even though I hit the tear button on the probe, the force probe, you can see here that it's not really at 0. All right? So if we don't select, look at how much different that number is. Right? We want to make sure we just select the part with the spike. Basically, we want to select the same part here as we see down here, right? Because they share the time axis. And then there's our area, and there's our change in velocity. Those are the numbers you'd write down. Go up to experiment, delete last data run, or use alt minus. It'll clear it off, and you do another one. It's so nice and simple. Okay. So that's how we're going to figure out the change in the momentum and the impulse. Okay. So the purpose of this lab, to create graphical and mathematical representations of the relationship between the impulse acting on the cart, the force acting over time, and the resulting change in the cart's momentum during a collision. Lab notes here. There's a file called Impulse versus Change in Momentum that'll look just like what I went through, except without data on it. It's, of course, on today's date on the website. Now, you're going to do a bunch of different collisions, okay? You'll do some using the spring plunger, which is the way it's set up right away, the cart. Some, you can use the magnet ends. You have to take the nub out of the force probe, screw in the magnet end, and then you have to turn the cart around. Right? So you have the magnets on magnets. That way you're doing a collision where they're not actually touching, which is kind of cool. And then if you come and get a clay cup from me, it's on the table in the middle of the room there, all right, you can run the cart into it and see what happens when it hits clay instead of hitting a spring or magnet ends. And that's going to be kind of cool to see what it does with that one. You want to do that one at least once. You can also, of course, change the velocity by how hard you push, and you can change the mass of the carts. Okay, you have extra masses you can put on there, so you can make the carts more or less massive. So all of those things are different kinds of collision. Spring plungers, magnet ends, clay cup, different masses, different velocities. So you're going to do a bunch of these and look for patterns. Now don't forget to zero or tear the force probe. There's a little button on the side of it. And your forces have to be between positive and negative 50 newtons. If it goes above 50, you push too hard, redo it, don't push as hard. All right? Don't use a trial where the force goes above 50. Otherwise, we can't guarantee that the force probe is accurate. There's electronic balances around the room or in the back of the room so that you can figure out the mass of your cart and your added masses, because that's one thing you got to list in your data table, because you need that to calculate the change in momentum. And then I have leveled the equipment and I've placed it against the wall. That way when it gets hit, it's not going to move the entire track. First time we tried to do this, we got a bunch of error because when it would hit the track, it would actually slide the track backwards, and so that would kind of change what was happening during the collision. Now we've got it pushed up against the wall, and I've tried to level it out so that you have as a little frictional effect as possible to try to make things more precise. And don't forget here, you're going to graph impulse versus change in momentum. Impulse on the vertical axis, change in momentum on the horizontal axis. Linearize it if need be. Go to the website, put in your slope. If it takes it, everything's good. If not, call me over and we'll figure out where you made a mistake. So I hope you've enjoyed this little pre-lab and you're ready to do this very exciting collision lab to figure out the relationship between impulse and change in momentum.